Welcome. Today, we're going to crack the code on metabolism. We're going to break down all those core pathways, the high-yield enzymes, and the clinical correlations you absolutely need to nail for step one. Let's do this.
So, what's the game plan? First, we'll lay out our metabolic blueprint just to get our bearings. Then we'll dive into what happens in the fed state, right after you eat, and then flip it to the fasting state. After that, we'll cover 2 essential side missions your body has to run. And finally, we'll tie it all together with the high-yield diseases that just love to pop up on exam day.
Okay, let's jump right in. First things first, we need a map for our journey. This is the metabolic blueprint, showing us exactly where all the magic happens inside the cell.
So check out this map. This is basically our entire metabolic world in one picture. And the first thing you have to get is this idea of compartmentalization. You'll see some pathways like glycolysis and the HMP shunt are hanging out in the cytoplasm. But others, like the TCA cycle and beta oxidation, they're tucked away inside the mitochondria. Seriously, knowing which pathway happens where is a classic exam question. So keep this mental map with you as we go.
All right, let's kick things off with our first scenario, the fed state. Picture this. You just had a big meal, your blood glucose is soaring, and the master anabolic hormone, insulin, is now in the driver's seat. Now, this is super interesting and, incredibly high yield. How does your body actually trap glucose inside the cells? It's all about these 2 enzymes. Hexokinase is in most of your tissues. It has a low Km, which means it has a really high affinity for glucose. It's basically always on, even when glucose is low. But then you have glucokinase, which is only in the liver and pancreas. It has a high Km, so it only really kicks into gear when there's a ton of glucose around, like right after a meal. This lets the liver act like a sponge, soaking up extra glucose. And don't forget, glucokinase has that high Vmax, and importantly, it's induced by insulin.
Okay, if there is one regulatory molecule you burn into your brain from this whole thing, make it this one. Fructose 2,6-bisphosphate. Think of it as the master switch, the traffic cop of metabolism. It tells the cell, hey, we're burning glucose now, or nope, hit the brakes, we're saving it.
Right, so how does this master switch actually work? It's all thanks to this clever bifunctional enzyme. In the fed state, when insulin is high, a phosphatase lops off a phosphate group. This turns on the PFK2 side of the enzyme, which starts cranking out our master switch, F26BP. Then, F26BP goes and powerfully activates PFK1, which is the big rate-limiting step of glycolysis. The bottom line? The green light for burning glucose is on.
All right, so glycolysis in the cytoplasm made us some pyruvate. Now that pyruvate travels into the mitochondria and meets the PDH complex. And listen up, because this part is absolutely critical. This step is a one-way street. It is irreversible. Once pyruvate becomes acetyl-CoA, that's it. There is no going back. You cannot make net glucose from acetyl-CoA. Got it? Good.
The boards love to test cofactors, right? Well, PDH needs 5 of them to work. And this mnemonic is a gift. The lovely coenzymes for nerds. That's thymine, lipoic acid, coenzyme A, FAD, and NAD. And here's a pro tip for you. These are the exact same 5 cofactors that alpha-ketoglutarate dehydrogenase needs in the TCA cycle. That's 2 for the price of 1. Super high yield. Okay, now let's flip the script. Hours have passed since your last meal, your blood glucose is starting to dip, and now glucagon is the one calling the shots. The mission has changed. We need to make our own glucose from scratch to keep the brain and red blood cells happy. So remember how we said some steps in glycolysis are one-way streets? Well, that means we can't just throw the whole process in reverse. We need a few special workarounds. Gluconeogenesis uses these 4 bypass enzymes to get the job done. You've got pyruvate, carboxylase, and PEPCK working together to get around pyruvate kinase. Then fructose 1,6-bisphosphase bypasses PFK1. And finally, the big one, glucose 6-phosphase, which is only in the liver, is the enzyme that lets that brand new glucose escape into the blood. You've got to know these 4.
Okay, pay attention because this is a classic exam trap. Can we make glucose from fat? Well, it depends. Even-chain fatty acids break down into nothing but acetyl-CoA, and we already said that's a dead end for making glucose. But odd-chain fatty acids give you 1 molecule of propionyl-CoA at the end, and that can be turned into succinyl-CoA and jump into gluconeogenesis. So just remember the mnemonic, it's odd that only odd-chain fatty acids can do it.
All right, time for a couple of key side missions. Think of these pathways as the special forces of metabolism. One creates protective firepower for our cells, and the other handles toxic waste disposal.
So what's the whole point of the HMP shunt?
It's all about making NADPH. And please, whatever you do, don't mix it up with NADH. They are not the same. NADPH is the cell's source of reducing power. It's used for things like building fatty acids. But, and this is huge for the boards, it's absolutely essential for protecting our cells, especially red blood cells, from oxidative damage. The rate-limiting enzyme you have to know is glucose-6-phosphate dehydrogenase, G6PD.
You know, when we break down proteins and amino acids, we get this nasty byproduct, ammonia. It's super toxic. The urea cycle, which happens in the liver, is our way of converting that toxic ammonia into harmless urea that we can just pee out. This mnemonic is an absolute lifesaver for the intermediates. Ordinarily, careless crappers are also frivolous about urination. That'll give you ornithine, carbamoyl phosphate, citrulline, arginosuccinate, arginine, and your products, fumarate and urea.
So why are we spending all this time on these intricate pathways? What's the point? Well, it's because when these pathways break, you get diseases. And these are the kind of diseases that are all over step 1.
Let's kick things off with a big one, G6PD deficiency. It's actually the most common human enzyme deficiency out there, and it's X-linked recessive. Without G6PD, red blood cells just can't make enough NADPH to defend themselves against oxidative stress. So when they're exposed to some kind of trigger, their membranes get damaged and they basically pop. When it comes to your exam, it's all about the buzzwords. If you see these, your brain should scream G6PD deficiency. You'll see Heinz bodies on a blood smear. Those are little clumps of denatured hemoglobin. You'll also see bite cells, which are literally where a macrophage in the spleen has taken a bite out of the red blood cell to remove that Heinz body. Then look for a trigger in the story, like a sulfa drug, an infection, or even fava beans, and you've got your diagnosis locked down.
Okay, this is a classic comparison they love to test. You've got to know the difference. Essential fructosuria from a fructokinase deficiency is totally benign. The person just pees out the extra fructose, no big deal. But hereditary fructose intolerance from an aldolase B deficiency, that's the bad one. Fructose 1-phosphate builds up, it's toxic, it drains the cell of ATP, and you get severe hypoglycemia and jaundice right after a baby is introduced to fruit or juice.
Hey, it's kind of the same story with galactose. Galactokinase deficiency is the milder one. It mainly just causes infantile cataracts because galactitol builds up. But classic galactosemia, a GALP deficiency, is way more severe. You get liver damage, intellectual disability, and here's a key association you can't forget, a massively increased risk of E. coli sepsis in newborns.
Just to hammer this home, ammonia is a neurotoxin. It's really, really bad for the brain. So when the urea cycle fails, either because the liver isn't working or there's a genetic problem, ammonia starts to build up in the blood. It zips right across the blood-brain barrier and wreaks havoc, causing swelling and messing with neurotransmitters by depleting key molecules like alpha-ketoglutarate. So in a clinical vignette, what are you looking for? Keep an eye out for a patient maybe with a history of liver problems who suddenly becomes confused and develops this characteristic flapping tremor called asterexis. That, plus things like slurred speech, is a classic presentation of hepatic encephalopathy from high ammonia. Treatment is all about lowering that ammonia load, using things like lactulose and putting them on a low-protein diet. All right, let's put it all together with a classic board-style question. We've got a 9-month-old with neurologic problems, poor feeding, and labs that scream lactic acidosis. They even tell you lactate and alanine are high, which is a huge clue that pyruvate is backing up. This is a dead ringer for a PDH complex deficiency. So the question is, what do we feed this kid? We can't give them things that turn into pyruvate, right? We need a fuel that bypasses the broken enzyme. We need a ketogenic fuel source. So we look at our options. Which amino acids are purely ketogenic? Well, that would be leucine and lysine. And there it is, B, lysine. It gets converted straight to acetyl-CoA, fueling the TCA cycle without making that dangerous lactic acidosis any worse. See how it all connects? Knowing the map, the control points, and what happens when things go wrong is your key to mastering metabolism. Thanks for joining me.